we took a major leap, and we arrived at the beautiful conclusion from Clausius inequality that there should exist a system property or a property of the system that is called entropy, and then that should in turn be equal to, or the change in entropy ds should then be equal to integral of dq by t internally reversible, right? So I'm going to write that down again, and then we'll start from there, and we'll go and see what is entropy generation. And we will see in this video that entropy gets generated. Unlike energy, which cannot be generated or destroyed, entropy can certainly be generated, and that the entropy of the universe is ever expanding or ever increasing, and that this has important implications for everyday engineering devices. So that's what we are going to do in this video, but we'll start from where we left, which is that ds equal to delta q by 2 t internally reversible, or delta s is equal to integral delta q by t internally reversible. There are a couple of important things to note about this expression here, and that is that supposing I have a state 1 and a state 2, and that I can reach state 2 from state 1 using any number of methods, any number of paths, right? And let's call this property 1, let's call this property 2, right? So I can take any number of paths to go from 1 to 2, right? But, and in each case I will have an integral dq by t, let's call this path A, path B, path C, right? For path A, the integral dq by t will not necessarily be equal to path B delta q by t, right? So all of these integrals need not be the same, right? Then how do I evaluate what is delta s? That's easy, because delta s is always evaluated through an internally reversible process. So here's the crux. The crux is that no matter how I go from 1 to 2, the delta s remains the same. That is, s2 minus s1 is the same irrespective of which path I take to go from 1 to 2. But to evaluate s2 minus s1, I need to use this one, right? And I'll repeat this. So because entropy is a property, it only depends on the state and not how I get to that state, which means the entropy at 1 depends only on state 1, right? And the entropy at state 2 depends only on state 2. It doesn't depend on how the system went from 1 to 2, right? And so although all of these integrals can all have different values, this integral will be equal to delta s. And this delta s will be the same irrespective of how I go from 1 to 2, right? Because this is evaluated over an internally reversible process. Whereas I can probably get from 1 to 2 using multiple processes that may or may not be internally reversible. So let us consider two processes from between states 1 and 2, one of which is internally reversible and the other may not be. So let us assume that I have a system that goes from state 1 to state 2 using through a process that is not necessarily internally reversible. So it's an arbitrary process, right? So this is an arbitrary process. It may be internally reversible or irreversible, doesn't matter, right? And then let us assume that the system, after reaching state 2, comes back to state 1 through an internally reversible process. So let me put arrows here. So this is let's assume that system returns to state 1 using this is an internally reversible system. process. So the system starts at 1, undergoes a process, an arbitrary process to reach 2, and returns from 2 to 1 through an internally reversible process. Because we started at 1 and ended up back at 1, this is a cycle, and so we should be able to write Cauchy's inequality for this cycle. So let's do that, and let's call cyclic integral of delta q by t should then be less than or equal to 0 for this whole journey from 1 to 2 through an arbitrary process, and then back from 2 to 1 through an internally reversible process. This whole journey, starting at 1, ending back at 1, this whole cycle, delta q by t integral should be less than or equal to 0. And I can break this into the two processes that constitute this cycle. One is the process from 1 to 2, and the other is the process from 2 to 1, right? And so from 1 to 2, I can write this as integral 1 to 2 delta q by t plus integral 2 to 1 delta q by t, and this should be less than or equal to 0. Now, let's look at 1 to 2, that's arbitrary process. So let's retain integral 1 to 2 delta q by t, but look at the second term. The second term is going from 2 to 1, and we know that that process is internally reversible, right? So I should be able to write this equation as integral 1 to 2 delta q by t plus integral 2 to 1 delta q by t internally reversible should be less than or equal to 0. Now we know that delta q by t internally reversible is equal to ds, and that integral 2 to 1 delta q by t internally reversible should be the change in entropy during that process, right? And so this should be equal to delta s 2 to 1. So this is integral 1 to 2 delta q by t plus delta s 2 to 1 less than or equal to 0, which means I can write this as delta q by t plus s1 minus s2. Why s1 minus s2? Because I'm talking about a process that goes from 2 to 1. So it's the final value minus the initial value. The final value being s1 and the initial value being s2, right? So this is less than or equal to 0, and so I can write s2 minus s1 as being greater than or equal to integral 1 to 2 delta q by t. And this s2 minus s1, because entropy is a state function, this s2 minus s1 I can write as delta s 1 to 2, because it's the final value minus the initial value, and it's a state function, so I can write it as delta s 1 to 2 should be greater than or equal to integral 1 to 2 delta q by t. Now we got an expression that is independent of whether we end up back at 1 or not. We got an expression that talks about an arbitrary process from 1 to 2, right? And we can say that the change in entropy during any arbitrary process 1 to 2 is then greater than or equal to 1 to 2 delta q by t, right? And this has an important implication which we will shortly see. So I'm going to get rid of this subscript 1 to 2, because if I have an arbitrary process going from 1 to 2, it's clear that delta s is s2 minus s1, which is delta s 1 to 2, right? So that's fine. So I'm going to just write delta s for any arbitrary process is greater than or equal to delta q by t integral for that process. So what does this mean? This means that the change in entropy of a system is always greater than or equal to the entropy that is transferred to that system. Why is this the entropy transferred to the system? Because this is the heat entering the system at the system boundary, right? And this as Professor Udipto mentioned in his previous video, is the system boundary temperature at which the heat enters the system. So which means that integral delta Q by T is the entropy that is transferred to the system during that process. Whereas the change in entropy of the system is greater than or equal to the entropy that was transferred to the system. Now, if you have a quantity that is increasing by more than what is transferred to the system, then there must be some entropy generation within the system, and that we will call S-gen. And so we'll just write delta S equal to integral dq by T plus S-gen. Right? This is entropy This is the entropy generated or the entropy generation term, and that basically makes the equality between, so this inequality turns into an equality for delta S. So delta S is equal to integral of dq by T, delta Q by T plus S-gen, right? Now, looking at these two, we can have some observations. What are these observations? These observations tell me that S-gen, because this is something that is added to this side, to make these two equal, this S-gen has to be greater than or equal to 0. Right? Because I'm making this inequality into an equality, so that means S-gen cannot be negative. That is, entropy generation can never be negative, irrespective of what process I have. And that's pretty significant because, as you're going to see in a little while, we are going to show that the entropy of the universe is always increasing, right? So let's summarize what we have until now. For a reversible process, we have delta S equal to integral delta Q by T, right? Because by definition delta S is equal to integral delta Q by T internally reversible. So for a reversible process, delta S is equal to integral of delta Q by T. For an irreversible process, delta S is greater than integral delta Q by T. Right? That's the inequality part of this equation right here. So correspondingly, S-gen for a reversible process is 0, and S-gen for an irreversible process is always greater than 0. So for any process, S-gen greater than 0 is an irreversible process. S-gen equal to 0, that means it's a reversible process. And S-gen less than 0, it's impossible. Right? So let's look at two common scenarios that we encounter using this right here. The first situation is for an adiabatic system or an isolated system. For an isolated system, there is no energy exchange with the surroundings, and so therefore delta Q should be 0. So delta Q is equal to 0. So which means that delta S is equal to integral delta Q by T plus S-gen. Then I have this term going to 0 because delta Q is 0. So delta S then should be equal to S-gen. which means that Sgen has to be greater than or equal to, sorry, delta S has to be greater than or equal to 0. This has a very profound effect or implication on the entropy of the universe, because we consider or claim or assume that the universe is an isolated system, which means that the entropy of the universe either remains constant or continues to increase, and that there is never a situation where the entropy of the universe can actually decrease, right? And this is why we say entropy of the universe is always increasing and that it never decreases. Now, there are a couple of things to remember when we say delta S of an isolated system is greater than or equal to 0. There's a common misconception that delta S of a system during a process can never be negative. This is not true. You can have delta S of a system less than 0. That's absolutely possible. For example, if I'm removing heat from a system, then typically I will have a delta S of the system less than 0, right? I can have delta S less than 0, I can have delta S more than 0, greater than 0. I just cannot have delta S of an isolated system less than 0. And for an isolated system, then delta S is always greater than or equal to 0, right? So I must qualify this for an isolated system. Let's come back and see what are the implications for a heat engine, for example. So before we do that, let's look at change in entropy for let's say as a special case, the temperature remains constant during a process. Then we will have delta S equals integral delta Q by T plus Sgen. I can, because this is constant, this can be pulled out from the integral, and so let's say T, which is constant, equal to T naught, then I can have 1 by T naught delta Q integral plus Sgen, and so that should be equal to Q by T naught plus Sgen. Right. So the delta S for an isothermal process is Q by T naught plus Sgen, right? Now, there may be ways in which we can add heat to a system at constant temperature in a reversible manner. A typical example is addition of heat to a thermal energy reservoir or the removal of heat from a thermal energy reservoir. So when that happens, because we assume that the thermal energy reservoir is at a constant temperature and that there is no temperature gradients within the thermal energy reservoir, we can then assume that the process happens infinitesimally slowly, infinitely slowly, and that Sgen is 0, right? So during an isothermal process, if Sgen is 0, in other words, if the process is reversible isothermal, process, then we will have delta S equals Q by T, right? So at the extreme case, when I have a reversible process and an isothermal process, then I can write delta S equal to Q by T naught, right? Now what is the implication for a heat engine? So if we have a heat engine that has temperature TH, takes heat QH, and operates in a cycle, and let's say that we have a reversible heat engine, then we have here TL, and this is QL, and this is W. So what we have here is that if we have a system that is, if I have a system considering only the high temperature reservoir, right? So I'm going to write the change in entropy for the high temperature reservoir, right? And let's call this delta S HTR is equal to QH divided by TH, because I'm assuming that this is a reversible engine and the heat transfer between the reservoir and the engine takes place reversibly, and even within the reservoir there is no temperature gradient, which means that I can assume that this is a reversible isothermal process for the reservoir itself. And so the delta S of the high temperature reservoir is then minus QH by TH, right? And similarly, the change in entropy of the low temperature reservoir is QL by TA. So why is it negative here? Because heat is being removed from this reservoir, so its entropy is decreasing, which means delta S for that system is less than 0. And here I have a low temperature reservoir to which heat is being added, which means its entropy increase, its change in entropy is positive, or its entropy increases, and that is should be equal to QL by TL if it is done in a reversible isothermal manner, right? And so if I take the entire system, then the change in entropy of the entire system consisting of the engine and the reservoirs together. So let's call this the overall system. And delta S of the overall system is delta S of the high temperature reservoir plus delta S of the low temperature reservoir. I'm not adding here the change in entropy of the engine itself, because that's operating in a cycle, and so over a cycle the change in entropy should be 0, because entropy is a state function. So therefore the delta S of the overall system is delta S of the high temperature reservoir plus that of the low temperature reservoir. So that should in turn be equal to right, and we know that this delta S of the overall system has to be greater than or equal to 0. Why? Because this overall system is not having any heat interactions with the rest of the universe, which means that the delta S of this system is got to be greater than or equal to 0, right? So which means that QL by TL it's got to be greater than or equal to QH by TH. And what that means is that QL by QH should be greater than or equal to TL by TH. And the equality applies when it is a reversible heat engine, and the inequality applies when it is an irreversible heat engine. And so this is an important implication for the operation of engines. And that tells you basically that as long as TL and TH have positive values, which they always do, then QL and QH should have positive values. That is, QL cannot be 0. That is, you cannot save the heat that is then rejected to the low temperature reservoir. It's got to be such that QL is by QH, or in other words, I can also write as QL has to be greater than QH times TL by TH. And that QL therefore cannot be 0, and so it reinforces again, or it comes back to the point of the Kelvin-Planck statement, which says that I cannot have an engine running in a cycle that operates with only one reservoir, absorbing heat only from one reservoir. So we come back to that and we say that you've got to have a positive QL, and that QL cannot be 0, right? So we'll end here.